electronic structure of atoms. Yesterday, we talked about how scientists were studying light, and we talked about how light behaves. We had these two realms on what we thought things fit into. They fit into the particle or mass category, or they fit into the energy or wave category. And those two realms did not meet, or at least that's how we saw it at that time. Light was one of those things we were looking at, and it didn't quite categorize as one or the other. We had experiments that showed it behaved like energy or a wave, and we had experiments that proved it was like a particle or matter. And that just didn't work out really well, and we had to kind of come to a consensus and say that light behaves as both a wave and a particle. It's called the wave-particle duality of light. We had to get Einstein involved in all of this, and you'll see how that kind of comes about. But since we're going to think of light as a wave and a particle, we have to know about waves and particles. So first we're going to talk about the waves. The parts of a wave, and this is our next question on the Cornell notes, on what are the parts of a wave. The first part is its wavelength. We have a wave here, and you can judge the wavelength of a wave by going from crest to crest. You can go from crest to crest, or trough to trough, or any one analogous point to another point on a wave. Crest to crest is generally easier than the others. And wavelength is represented by the Greek letter lambda. Okay, you can draw that one with a little squiggly and then a kickstand. That's kind of how I draw it. It's kind of fun to say. You should try it. Lambda. Lambda. Okay, and that's wavelength. So I want you to write down wavelength. It is lambda, and it is measured in length measurements. So measured in meters or nanometers. When we're talking about light, it's usually going to be nanometers. Along with wavelength, the other thing that we have is frequency. If I talk about frequenting the library, what does that mean? That I go there very often, okay? I frequent that library. Frequency is how many waves happen in a certain given period of time. So second is a good one. So how many waves per second or cycles per second? It is going to be measured in hertz, which is 1 cycle per second. So I want you to write down measured in hertz. And hertz is often abbreviated Hz. Because we don't generally use cycle or wave as a unit, basically what a hertz is 1 over second. Whatever per second. Now, often you will see that expressed as s to the negative 1 power, because anything to the negative 1 power is 1 over that thing. And that's from 8th grade math. That's why you learned it. I know it's a long time ago, but don't freak out if you see to the negative 1. You know it means 1 over that thing that's raised to the negative 1 power. Now, oftentimes, frequency should always be expressed in hertz. But if you're working with hertz in a math problem, it's easier to work with as 1 over second. So it just depends on how I'm working with those as to whether I express it as hertz or 1 over second. Okay, we're actually going to skip that next line and go to the next question, which is what is the relationship between wavelength and frequency? All right, so and frequency is measured by V there. If I have a wave, and let's say what you see on the screen is 1 second, 1 second of time, and you can think of these waves as like waves of the ocean, all right, maybe hitting a pier or something like that. If I have a higher frequency, so more waves in this given period of time, what happens to my wavelength?
Shorter.
Okay, it gets smaller. So as frequency goes up, wavelength goes down. Now, if that makes a lot of good sense to you, write that down. What kind of relationship is that? And you should know it. So one variable increases, the other decreases. So, an I. Proportion. What kind of proportion? Inverse. Inverse proportion. That's why we studied that in that first chapter. Yeah? Okay. All right. You must know, and a lot of these questions that I put on these Cornell notes, I sat down with the state curriculum. This is the stuff that they're going to expect you to know. This is the stuff they're going to put on that MSL. Okay. So if I increase my frequency even more, what happens to my wavelength? It gets even smaller. So again, as frequency goes up, wavelength goes down. Okay, now we'll go back up to what is electromagnetic radiation. It sounds awful, doesn't it? Yeah, like something that'll kill you. Well, a lot of times we hear that term, and the word radiation comes with some bad connotations. We think about things, nuclear radiation, and that kind of harmful stuff. Electromagnetic radiation, though, what we're talking about there is it's radiating from something. Just like a radiator radiates heat. Okay? Radiators aren't necessarily dangerous unless you trip and fall and bust your head open on one of those. Now, electromagnetic radiation is energy with wave-like behavior. It is electric waves and magnetic waves moving at 90-degree angles to one another. Okay? So, electromagnetic radiation is energy with wave-like behavior, or anything that travels through space as a wave. Lots of different types, and they're not all dangerous. This is on the back of that other handout that I gave you that I told you would be, is a copy of the chemistry reference tables. And you can see that we have radio waves. That's a type of electromagnetic radiation. TV waves, they're in here somewhere. Microwaves. Infrared. Now, what's infrared? Do you know? Heat, exactly. You know, if you have to wear infrared goggles, it's those heat-sensing goggles. If you watch movies like Predator, where they have to, the predator only sees by heat, and so they put on the infrared goggles so they can see how the predator sees. Then Arnold Schwarzenegger covers himself in mud to disguise himself from the predator. It's a pretty awesome movie. You should watch that. Okay, now, so that's heat. Now, you can't see heat. It's not part of our visible spectrum. But sometimes you can see the distortion that the infrared waves cause. Think about on a hot summer day, and you're looking out over a car, or you're looking at like a metal grill. And if you just look right at the top of it, you can see the distortion of the heat waves. You guys have experienced that? Yeah? Okay. We can't really see it. We can just see the distortion. Now, the visible spectrum is the only part that our eyes can discern. Now, from wavelength, it's only a small amount. And the handout that I gave you, you can see how tiny that section is. It's only about 300 nanometers long. We can see from 700 nanometers to about 400 nanometers, and that's about it. That is our visible spectrum. That's all our eyes can detect. And again, that is split up into Roy G. Biv, and on your handout it has it kind of expanded out there. Then we go to ultraviolet. Our eyes also can't really see this. We see it a little, we can see the distortion from it, like white t-shirts. White t-shirts, if you just take cotton and bleach it, it becomes white, but if you put it up next to a t-shirt that you would buy in the store, it would look dull in comparison. Because the t-shirts that you buy in the store is bleached cotton with an added optical brightener. And that optical brightener glows in the ultraviolet region. We can't see that, and our eyes just give us the perception of really bright white. And that's what all white t-shirts are sold with now, because otherwise it just kind of looks dingy and dirty to us. even though it's bleached white. It just doesn't have the optical brightener on it. Then you have your X-rays and you have gamma rays. Gamma rays, well, X-rays aren't necessarily dangerous. You can have quite a few of those in a year and be just fine. But what does the technician do when you have an X-ray? Okay, puts the thing over you to protect the reproductive organs and that sort of stuff. But what else? Then they get out of there, right, before they turn on the X-ray. And that's because they're there day in and day out, and that would be too much exposure for them, even though it's safe for you to have several X-rays. That's their day-to-day job, and that would just be too many. Now, gamma rays are given off by the sun. Those are pretty dangerous. They will cause damage on a molecular level. The sun that is a byproduct of nuclear fusion, which was what happens on the sun and gives us our heat and light. It also gives all of these gamma rays, which are hurled toward the Earth. We're protected by the Earth's magnetic field. So, yay, magnetic field. All right? Otherwise, you might have kids with hands sticking out of their forehead or, I don't know, other weird things like that. But it'd probably kill your reproductive organs first. So, yeah, right. Now, these are all the different types of electromagnetic radiation. So light, or visible light that we see, is a part of that, as well as heat, things that you may not have thought of before. Now, if you look at the handout that I handed you here, it has wavelength and longer wavelength over here at the radio waves. And up here on the board, you can see it more visually. And then over toward gamma rays, you have a shorter wavelength. What's the relationship between wavelength and frequency? Okay, fantastic. So the types of questions that you can get, now you're going to have this as a reference table, but it's not going to say, please turn to the back of your chemistry reference tables and look at the electromagnetic spectrum to answer the following. It's not going to say that. It's just going to ask, which one has a higher frequency, radio waves or X-rays? The table doesn't tell me about the frequency, it only tells me about the wavelength. So, longer wavelength would mean what kind of frequency? Okay, smaller frequency. And shorter wavelength would be higher frequency. So that's how they're going to test your knowledge of that relationship. So which one has a higher frequency? X-rays. All right? X-rays have very high frequency, and we're going to find they have high energy as well when we talk about that other relationship. Okay. Oh, they could also do it with colors of light. Which one has a higher, well, which one has a lower frequency? Orange or blue light? Look at the table. Okay. Orange is the side with longer wavelength, so it's going to have a smaller frequency. Does everybody see that? Any questions on that? Okay. Awesome. Now, in dealing with the wave, you have this equation on the flip side of that paper we were just looking at. We can look at the relationship between wavelength and frequency. C is commonly known as the speed of light. That's not what I have written on that piece of paper. I have speed of electromagnetic radiation. That electromagnetic radiation covers all of them. Heat, light, it all operates off of the same speed as long as they're traveling through the same thing. As long as they're all traveling through air or they're all traveling through space. Okay? They all travel the same speed. We commonly know that speed as the speed of light. Okay? But it's not just visible light. It's all of those that we just talked about. And it is one number, 3 times 10 to the 8 meters per second. So C is one number. If wavelength goes up, what does frequency have to do? Because they have to multiply to give this number and no other number. It has to go down. All right, so another way you can look at a math problem and tell the relationship of those two. All right. Like I said before, we're not actually going to work through these problems, even though they are in this PowerPoint. That was fun for honors. Okay. This skips all the way to the bottom of this particular page on your Cornell notes. And it says, what are the experiments that prove light's wave-particle duality? All right, the first one that we're going to look at is how is light like a wave? Evan, could you turn off the lights for me, please? Let's look at. Okay, so we can think of this little animation as think about water. All right, we've got water on this side, and a wave is going to hit this wall, which is in pink. And there's a hole in the wall. And we're going to see what happens to that wave when it hits this slit in the wall. Okay, just like dropping a pebble in water. You create all of these other waves, and it kind of radiates out from that one place. Well, the experiment that proved that light was a wave is called the double slit experiment. So I want you to write down next to that part where they're asking about the experiments, I want you to write down wave, double slit experiment. It's right here. Wave, double slit experiment. All right, right now we're only looking at one slit. Now let's look and see what happens when we have two slits in this wall. Basically, when that wave hits each of these holes in the wall, it is going to create the same sort of pattern. But pretty soon the patterns start to interfere with one another, and you get different results. So let's look at the double slit experiment. Here it goes. There's our wave. It hits, it starts radiating out, and now you start to see that interference. Where you have two crests of a wave meet, you get a supercrest. Where you have two troughs meet, you get a supertrough. Where you have a crest meet a trough, flat space. All right, so if we looked along this wall right here, we would have high waves, flat water, high waves, flat water, high waves, flat water. And it would be this pattern across the back wall. If instead of thinking about water, if we took a flashlight and from where this wave is originating, we shine that flashlight at this wall with two slits, you wouldn't just see two beams of light project on that back wall. What you would end up seeing is exactly what you see here, except in the form of light. You would see really, really bright bands of light and dark bands. Bright band, dark band, bright band, dark band. And it would create that pattern. That is the experiment that proved that light behaves as a wave. All right. Now, for the light as a particle, we have the photoelectric effect. So, again, around that same spot, what are the experiments that prove light's wave-particle duality? Particle, I want you to put photoelectric effect. Now, with the photoelectric effect, they were doing some very fascinating experiments. Really. They were shining different colors of lights on metals. Red light, bright red light, green light, bright green light, and would leave it there. And what they were looking for, they had these metals hooked up to an ammeter, something to measure the electricity. Because if electrons move, that is electricity. And so they were trying to make electricity by shining lights on metals. So they shined a red light, and nothing happened. A bright red light, nothing happened. Green light, nothing happened. Bright green light, nothing happened. Only when they got to blue. When they got to blue light, if they shined it on a metal, electrons would start to flow. And if they shined a bright blue light on that metal, more electrons would flow. Purple would be the same thing. Now remember, they have different frequencies there. and purple and blue have higher frequencies than the other colors. And basically it says that no electrons are emitted if the light's frequency was below a certain minimum, no matter how long they shine this light on there. And the way this proved that the way that they proved that light was also a particle is that something had to be hitting that metal, knocking the electrons off. There had to be something there that was hitting it. And that is what proved that light was also a particle. All right, with that blue light. It had to be of a certain energy, though. Okay, so now we have our experiments. We'll kind of fill in the rest of this. Now, that photoelectric effect, like I talked about yesterday, disobeyed the wave theory. And was explained by the scientist Max Planck. He got involved and said, well, maybe light just isn't just a wave. He said that energy is emitted in small amounts, and this is how he explained it, small specific amounts called quanta. One of our questions is explain the term quanta. It's not really a question, but a command. What is it with a question mark on it? So quanta is small specific amounts of energy. They're in these little packets of energy, and they correspond to electrons and their energy levels. Now what this says is we can have packets of energy, we can have 3 packets of energy, we can have 12 packets of energy, but we can't have half a packet. They have to be in these specific amounts, not anywhere in between. Now this term quanta, again, is where the word quantum, quantum numbers, quantum mechanics, quantum physics, all of that came from. Now, this is Planck's equation. This is on that other sheet of paper. It's in a box. And it is the relationship between energy and frequency. Now, H is Planck's constant, and it's a pretty little one here, times 10 to the negative 4 joule seconds, so it has weird units. But that's a constant, and that number, that H, never changes. E is energy measured in joules. You're probably not used to the term joules. You're used to the English unit version of that, which is a calorie. You know what I'm talking about now? Okay, it's how much energy you have to expend to burn off your food. It's how many calories are in, like, a granola bar. All right? A joule is just the metric term for that. All right, and V is frequency, just like it was in the last one. Now let's look, because one of our questions is, what is the relationship between frequency and energy? Now, H never changes. If frequency goes up, what happens to energy? H never changes. If frequency goes up, what happens to energy? It goes up too. What kind of relationship is that? Not inverse like the other one, but direct. Fantastic. All right? As one variable goes up, so as frequency goes up, energy goes up. You need to write that down on your Cornell notes. I've got it. What is the relationship between energy and frequency? And that's still on the front. Okay, if you look again at that other paper, at that electromagnetic spectrum, another way they can ask you about this relationship, they can say, which one has higher energy, blue or orange light? Well, what they have here is wavelength, right? So, longer, we don't know the relationship between wavelength and energy, but wavelength and frequency. Blue has a shorter wavelength, so what kind of frequency does it have? Higher. And higher frequency is directly related to higher energy. Fantastic. All right? And that's the type of questions they're going to ask you, not just what the relationship is, but ask you to apply it. Does that make sense? Okay. Okay, we get Einstein involved. I told you he was there. He expanded on Planck's theory and introduced the dual wave particle theory of light. Said that it's not either or, but both. It is, we can see light as a particle wrapped in a wave of energy. And that's the same way we view an electron. It is a particle because it does have mass. It's not very big, but it does have mass wrapped in energy. And that's how we see electrons. And he united two realms with this equation. Now, E equals mc squared, that just screams sciencey, doesn't it? People put it all over the place to mean science, and they have no idea how amazing this equation is, or what even it stands for. E is energy, M is mass. C is that speed of electromagnetic radiation, that 3 times 10 to the 8 meters per second. That simple thing, remember, we thought there was matter, the realm of matter, and the realm of energy, and those two did not meet. With this equation and Einstein's ideas, we saw that matter can be converted into energy, and vice versa. Matter being converted to energy, that's what happens when we split atoms. We split atoms, there's a slight loss of mass, but it's not lost. It is converted to major amounts of energy. And that's how we have enough energy to power lights of an entire city just by splitting atoms. That's also how we can destroy entire cities, by igniting critical mass for nuclear bombs. But E equals mc squared, that's what it means. It changed our whole paradigm on how we thought of the world, that they could be converted from one to the other. All right. Now, Einstein did come up with this idea of a photon, and that is a particle with a quantum of energy. Those packets of energy we call as photons. Now, I'll refer to photons here in a little bit, and you do have to know what a photon is. So, just a particle that has an energy with it. I know it's not a question on there, but you do have to know what it is.